So my project is based on a compound or group of compounds known as PFAS or PFAS for short, and I will be discussing the environmental fate, toxicity, and treatment of these compounds. So as an introduction, PFAS or perfluoroalkyl substances are fluorinated organic compounds found in many different types of products. They're most abundant, or the most abundant chemicals within this group are PFOA or perfluorooctanoic acid and PFOS, perfluorooctane sulfonic acid. And both of these chemicals are currently being studied because of their vast abundance in the environment and in humans. And the two chemicals are shown below. They're long organic chains or carbon chains with fluorine atoms attached to all of the carbons, and then usually there'll be a functional group on the end like a carboxylic acid or a sulfonate group in this case. For contaminant sources, PFAS compounds are utilized in numerous products requiring resistance to water, grease, stains, and they also have friction reduction properties, and those properties are very useful in high-tech industry such as in aerospace, the automotive industry, construction, and electronics production. Consumer products include Gore-Tex, Teflon, food packaging, firefighting chemicals, and carpet materials. The majority of PFAS exposure occurs due to continuous contact with consumer products, but exposure through drinking water is another viable exposure source that is becoming more of a concern. Sources of surface water contamination include aqueous film forming foam or AFFF runoff from firefighting activities, industrial runoff from processes that use these compounds, and effluent from wastewater treatment facilities. Groundwater contamination is also possible with these chemicals, and that can come in the form of landfill leachate, AFFF plumes, and wastewater biosolids application on land. In terms of environmental transport and fate of these compounds, they are resistant to environmental degradation because of their high chemical stability. And this stability is usually the reason these products are put into consumer products, but it does have a negative effect on the environment as they will not degrade. This environmental persistence can be attributed to the protection of the carbon atoms on the perfluoroalkyl chain. And this can be shown through shielding effects conveyed by the fluorine atom. So the fluorine atom will essentially protect the carbon atoms from degradation. And also the bonds, the covalent bonds between the carbon and fluorine atoms require very high energy input to break. So both of those mean that these compounds are very difficult to degrade via natural processes like hydrolysis, photolysis, and biodegradation using microorganisms. Continue with environmental transport and fate. PFAS environmental transport relies on environmental media interaction with the contaminant after emission into the environment. So there are three kind of media sources that will allow environmental transport, and those are through the atmosphere, through water, and through soil. Beginning with the atmosphere, atmospheric partitioning involves adsorption by raindrops or particulate in the air. And the environmental persistence we just discussed allows for long distance transport through the atmosphere, and this has even been shown to have detectable levels in the Arctic, so clearly these chemicals can travel very long distances in the atmospheric model. Residence times are approximately 10 days, and removal from the atmosphere involves wet deposition. So like a rain event will usually wash these chemicals out of the air and deposit them, into a water body or onto land. So once the compounds reach land or water, they can migrate and they can travel as well. So in water, they can be introduced either through wet deposition or direct contamination. And they are also resistant to oxidative processes in water environments. So this means that these compounds will likely bioaccumulate in aquatic systems. For soils, PFAS are also mobile in soils, and this is usually from the inability to form suspended solids. So these compounds cannot latch on to soils and be kind of permanently fixed. So they're able to migrate through the soils and typically into groundwater sources. Some sources of contamination in soils could be storage of industrial waste lacking adequate containment, biosolids applications from wastewater treatment, and atmospheric deposition can also contaminate soils and groundwater. And the soil mobility and transport in water, both of those characteristics of PFAS usually come from their physical properties, and those are low volatility, high water solubility, and low absorption to solids. So this allows them to move through soils and water quickly and to bioaccumulate and collect. PFAS can then be introduced into the food chain through plant uptake, through the root system. And the uptake rates rely on the PFAS chain length, so the number of carbon atoms, and the soil salinity and the temperature. So shorter chain PFAS compounds were shown in studies to easily migrate to plant shoots under increased salinity and temperature conditions. Once these compounds are able to enter the shoots, they can then be consumed by animals or herbivores, and that way they enter the food chain and can be consumed by humans. Studies have been done in the US, Japan, Norway, and Ireland, and they were studies just to find out approximations of how much of this stuff is in the environment. So air sample concentrations range from 1.54 to 15.2 picograms per cubic meter. The maximum water concentrations of PFOA were at 56 micrograms per liter and PFOS at 27.5 micrograms per liter. And in soil samples, the average concentration was 17 to 1,410 nanograms per gram for PFOA and 3.86 to 3,890 nanograms per gram for PFOS. So clearly, in soil samples, there's a very vast range of concentrations that you can find there. So moving on to the toxicology of these compounds, the primary route of exposure is ingestion of contaminated foods and water, or through ingestion of PFAS found in consumer products. Approximately 98% of the U.S. population has detectable concentrations of PFAS in the bloodstream, and this is usually in the low to mid parts per billion concentration range. And this shows that these compounds are able to bioaccumulate in the body. Once in the body, PFAS can be distributed from the gastrointestinal tract into different parts of the body. So the highest bioaccumulation concentrations are typically found in the liver, kidneys, and blood. PFAS interacts with the hydrophilic for PFOS or hydrophobic PFOA sites on protein albumin, which is found in the blood, and this allows it to be transported and distributed throughout the body after it migrates from the gastrointestinal tract. And typically, PFAS is found in organ systems with high renal blood flow. So the liver and kidneys receive a substantial amount of blood flow. And so those are the organ systems that are typically at most risk of being exposed to these compounds as they circulate through the body in the bloodstream. And then the transfer from the bloodstream to these organs is typically done with through interactions with membrane transport proteins. So PFAS compounds can mimic other types of chemicals that interact with these proteins and can enter these organs through that mechanism, through that biochemical mechanism. Metabolism of PFAS has not been shown to occur in many studies, and this is because of that biochemical stability. These compounds will not break down in the body, so they will keep circulating and bioaccumulating in the body. They can be excreted, however, so residence half-lives for these compounds, PFBA, which is another one of these compounds, has residence time half-life of 70 to 80 hours, and this one has a shorter carbon chain length. PFOS and PFOA have residence time half-lives of 2 to 6 years, and this is due to their longer carbon chain length. So the chain length does affect how easily the body can excrete these compounds. Typical excretion pathways for PFAS include primarily the urine and breast milk. So urine excretion rates have been calculated at 0.3 to 3.3 milliliters per day for PFOA and 0.1 to 1.5 milliliters per day for PFOS. In terms of the toxicodynamics, the primary effects shown in laboratory studies suggest that liver, developmental, and immune toxicity occur. And there are several toxicity mechanisms that are currently being researched, but the primary mechanism has to do with a receptor known as PPARA activation. So PPARA is a nuclear receptor that interacts with DNA to mediate a spectrum of biological responses in the body. And the toxicological effects of this increased activation of PPARA include increased oxidative stress at the cellular level, deregulation of mitochondrial activity, and inhibition of gap junction intercellular communication, or the ability of cells to communicate and move chemicals between each other. So clearly these compounds have a significant impact on the biochemistry of the body, and that leads to significant toxicosis, and that can be acute and chronic. For chronic toxicity animal studies, the results showed that the no observed adverse effect limit, or NOAEL, was found to be 2 milligrams per kilogram for male rats and 0.14 milligrams per kilogram in female rats. And so this showed that there is some sensitivity to PFAS in terms of the gender differences between males and females, and this can also be expected in humans. And PFAS was not expected to cause genetic disorders, but it was shown to cause developmental effects in fetuses if the mother ingests high concentrations of PFAS. So hepatotoxicity, or liver damage, is the primary symptom of both acute and chronic exposure. Neurotoxic effects were also observed through the disruption of calcium-dependent signal molecules in the hippocampus during fetal gestation, and this could lead to developmental problems with the fetus. Immunotoxicity studies also revealed increased doses of PFAS could change inflammatory response, cytokine production, reduction in weight of lymphatic organs, and suppression of antibody synthesis. So switching gears to water treatment and to remove these compounds from water, the 4 most effective treatment options for removal of PFAS in drinking water include activated carbon, anion exchange, membrane filtration, and advanced oxidation processes, also known as AOPs. So studies have been conducted showing that activated carbon is the most effective treatment technology because it is able to remove organic contaminants using both physical and chemical processes. So for physical capture, activated carbon consists of heterogeneous pores of varying sizes, and this allows the capture of molecules with varying molecular weights. Chemical capture deals with the activation process of char material, which forms functional groups like carboxylic acids, phenolic hydroxyl, and quinone carbonyls, which change the surface charges and hydrophilicity of the activated carbon, and this allows for efficient organic contaminant removal. So activated carbon comes in two types. It can be in granulated activated carbon, or GAC, and this is a fixed media surface with water flowing over or through the carbonaceous material. It can also be powdered activated carbon, or PAC, PAC, and this rapidly mixes in water to react with contaminants to create clusters of flocks or groupings of particles that become heavy enough that they settle out of solution, and these particles can then be collected and disposed of properly. Studies have shown that 39% PFAS removal with GAC was obtained, and this lower number was typically because contamination needed to be, or to effectively remove the contaminants, reactivation was required, and so this was a frequent operation that was required, and this reduced the efficiency of GAC usage. In contrast, PAC removal efficiency was found to be about 95%, and this was attributed to greater absorption capacity from high surface area and for the greater interaction of micropores and functional groups with the contaminants. So in summary, PFAS compounds are currently used in numerous products in both consumer and industrial applications. These compounds don't degrade in the environment and can therefore bioaccumulate, especially in water, due to chemical stability of these molecules. Human exposure is typically through ingestion of contaminated food, water, or handling of products made with PFAS compounds. Toxicology studies show that hepatotoxicity, developmental toxicity, neurotoxicity, and immunotoxicity can occur from both acute and chronic exposure. PFAS are recognized as contaminants of emerging concern, or CSC, by the EPA, and this is attributed to studies showing the toxicity and bioaccumulation effects of these compounds. The EPA, as such, has recommended a maximum drinking water level under 100 parts per trillion. This isn't an MCL, but this is a recommended level because of some of the findings that are now coming out. And this classification of compounds is another good example of why environmental impact studies should be required and are important whenever new products and chemicals are created, because we never know what kinds of effects they're going to have on the environment. In this case, these chemicals do not biodegrade at all in the environment, and this is a major problem in trying to remove these compounds from the system. Thanks for your attention.